Hello, everybody. My name is Juspreet Sandhu. I'm a final year PhD student in computer science at Harvard University, and I will be presenting our result on random Max-CSPs inheriting algorithmic hardness from spin glasses at ITCS this year. This is joint work with Chris Jones and Kunal Marwaha and Jonathan Shi. Kunal Marwaha is at U Chicago, Jonathan Shi is at USC, and Chris Jones is a postdoc at Bocconi. All right, so the motivation for this result is basically to understand the ramification of a recent line of beautiful work that links the solution space geometry of random instances of various families of combinatorial optimization problems to the success or failure of large families of algorithms. And in particular, the motivation for this work can be seen as trying to understand where do typical instances of random Max-CSPs in certain regimes fit in this story. So whether the solution space geometry of these random Max-CSPs can be analyzed, whether we can understand what the optimal value of the number of satisfied fraction of clauses of typical instances of random Max-CSPs are, and how these insights can say something about the ability for certain families of algorithms to succeed or fail on them. So to give you a brief idea, let me quickly mention three results. The first was that in the spirit of such results, the max cut of sparse random hypergraphs, when these hypergraphs of large degree, cannot be approximated better than a certain constant by local classical and local quantum algorithms. And in a similar flavor, the maximum independent set of sparse random graphs where the degree is large cannot be approximated to better than a certain constant, again by local classical and local quantum algorithms. So these results, for instance, give us a flavor of this program on the side of combinatorial optimization problems, but they really come from ideas that first started in spin glass theory. And let me mention these results, the two most critical results for our purposes in this area. The first is that ground states of certain so-called mean field spin glasses cannot be approximated to better than a certain constant by a stronger family of algorithms called low-degree polynomial algorithms. Low-degree polynomial algorithms, for instance, are known to subsume approximate message passing with bounded rounds, certain families of spectral algorithms, as well as many natural Markov chain Monte Carlo type algorithms. And in another area of the literature in high-dimensional inference, they're also conjectured to be as powerful as low-degree relaxations of the sum of squares hierarchy. All right. By far, the most important result that motivated our work or is connected to our work, in addition to this result by CLSS, is a tour de force result by Huang and Selke that showed that a precisely characterized family of algorithms called overlap concentrated algorithms can only output solutions with quality no more than a certain specific explicit constant on almost all instances of mean field spin glasses. And furthermore, there is actually an approximate message passing algorithm that can come arbitrarily close to this threshold with a bounded number of rounds. If the solutions of these mean field spin glasses have a very specific solution space geometry, which is called a branching overlap gap property, or a BOGP for short, then the value that can be achieved by these so-called overlap concentrated algorithms is strictly less than the optimal value. Additionally, in a prior paper by Cheating, Peter, Jonathan, and myself, we also conjectured that sparse random Max-CSPs, almost all sparse random Max-CSPs should have OGBs. And this conjecture was motivated with a version of the overlap gap property, which in fact is weaker than the one that was shown by Huang and Selke to hold for mean field spin glasses. And note that the conjecture is only for Max-CSPs and not CSPs. In particular, our results don't apply to CSPs because the unified connections between Max-CSPs and spin glasses we show turn to break down for technical reasons. All right. So this conjecture over here was based on the observation that a very prominent and important technique in mathematical spin glass theory called the Guerra-Toninelli interpolation had already previously been used to connect the optimal value of certain Max-CSPs to associate spin glasses. For instance, it was known that the maximum cut of random deregular graphs when the degree was large but constant could be related to the ground state energy of the Shenton-Kirkpatrick model spin glass. It was known that the max cut of sparse random hypergraphs when the degree was large could be related to a mean field K-spin glass. And one way to interpret one of our results is that we generalize the GT interpolation with ideas from the analysis of Boolean functions to understand the optimal value of any sparse random max CSP by looking at the correct associated spin glass. Now, a resolution to the conjecture mentioned above would immediately imply that local classical and local quantum algorithms are obstructed on almost all instances of almost all max CSPs. And in fact, not only are they obstructed, they cannot do better than ALG. And the reason for this is that CLSS showed that local classical and local quantum algorithms continue to be overlap concentrated in the sense defined by Huang and Selke. All right. So now let me informally state the two main results we have. And then we'll introduce the formal notions to understand them in detail, and I'll sketch some of the proof ideas briefly before concluding with some open questions. All right, so the first main result is that one can actually understand the optimal value of any sparse random max CSP by looking at the ground state energy density of the appropriately connected mixed spin glass. So let me briefly introduce how to sample an instance of a sparse random max CSP. Fix a predicate. This is the predicate that will act on your clauses. Each clause will have width k. Choose your clause to variable density alpha to be sufficiently large so that you are in the unsatisfiable regime. Then sample alpha n clauses independently and uniformly at random from the set of all width k clauses. Furthermore, in these width k clauses, every variable must be signed randomly, so it can appear as itself or its negation. Let V sub I denote the maximum number of fraction of clauses that can be satisfied for any choice of input of such an instance I, where I is sampled from the procedure above. Then, with high probability, as the number of variables get sufficiently large, the optimal value of the CSP, or the maximum fraction of clauses that can be satisfied by any assignment, will converge to the fraction of clauses that can be satisfied by a random assignment, plus a precise second order correction that diminishes as order 1 over square root clause to variable ratio. And this precise constant in the second order is given by the ground state energy of a spin glass that is parameterized by a so-called mixture polynomial that we will see shortly. And this mixture polynomial is chosen to be the noise stability polynomial of the predicate F minus its constant term for recentering. So the precise thing that this theorem tells you is that for any sparse random max CSP, you can compute the optimal value or the maximum fraction of assignments that can be satisfied by maximum fraction of clauses that can be satisfied by an assignment to second order precision by looking at the right spin glass. So the second theorem strengthens this result to have algorithmic implications, as we promised you. It says that not only are the optimal values the same, but if we look at good solutions to both this max CSP, the typical instance of a max CSP, and the spin glass, the overlaps between good solutions have the same support. And if this is the case, one can see them as having the same solution space geometry. And this is what it means to look at the solution space geometry of these combinatorial optimization problems. And we can basically bring back the framework of Huang and Selke from spin glasses to max CSPs to then assert that all overlap concentrated algorithms cannot achieve a solution quality that is better than a random assignment plus a precise second order deviation. The second order deviation is given by ALG, where ALG is exactly the threshold given by Huang and Selke. Furthermore, this ALG is strictly less than opt when there is a branching overlap property. So let me state two precise corollaries of these results that immediately lead to partial resolutions of prior conjectures in the literature. The first corollary is that all sparse random max CSPs where predicates have Fourier weights only on even levels greater than or equal to 4 have a branching OGB. The reason for this is that the corresponding spin glass, the way the Guerra-Tornelli interpolation sets it up, has a mixture polynomial that is known to be associated with a branching OGB, and that is known due to a confluence of results in Huang and Selke in CGPR19. So this partially resolves the conjecture that I stated prior, where the conjecture was that most max CSPs would have it, but well, at least we show that this family of sparse random max CSPs have some form of an OGB. The second corollary that resolves, perhaps not a conjecture, but a question in the thesis of Huang, is that local classical and local quantum algorithms cannot do better than to the explicit bound stated in theorem 2, which is this. on almost all instances of random Max-CSPs where predicates satisfy this constraint. So this resolves a question in Huang's thesis, where Huang wonders or proposes the question as to what generality do these OGP-based obstruction results on Max-CSPs hold. So it should be clear the reason that you can rule out local classical and local quantum algorithms immediately is that it was demonstrated in CLS 2022 that these algorithms are overlap concentrated. And to demonstrate that an algorithm is overlap concentrated, it suffices to show that it is approximately Lipschitz in a suitable sense. So we're now in a position to introduce the formal definitions and proof sketches, but I'd like to, before I proceed, I'd just like to reiterate that our results do not extend to random CSPs. The max part is critical. So here's some formal definitions. The model of sparse random max CSPs we work with is denoted as CSP alpha F. F denotes the predicate. It acts on every clause. The clause has width k. Alpha is suitably large. It gives the clause to variable density. An instance I of this is chosen as follows. Choose alpha n clauses uniformly and independently at random. Every clause has k variables which are independently randomly negated. Vi denotes the maximum fraction of satisfied clauses for the instance I under any assignment. Later on in the proofs, we will work with the number of clauses being not exactly alpha n, but being a random variable r that is sampled as Poisson alpha n. This does not quantitatively change the behavior of the system, but it is convenient for analytic purposes. A spin glass is parameterized by its mixture polynomial, denoted as psi, and it is a dense, random, non-homogeneous polynomial of degree k over the hypercube. So those are a lot of words. Perhaps a combinatorial interpretation of this gigantic equation is as follows. A spin glass is just a particular kind of dense random CSP on the hypercube. What is it specifically? It is a weighted linear combination of max cuts over complete hypergraphs where the cut is over interactions that can have random values, both negative and positive. So the way to see this is that there are k terms, each corresponding to a degree. You sum over the complete hypergraph with hyperedges of size I, and you slap a random and independent interaction as a standard Gaussian on every hyperedge, and you scale them to have equal contribution, reweigh them by a constant alpha I, and sum them all up. So the mixture polynomial is specifically given as the sum of the squares of the coefficients, the weighting coefficients, times a power of this S parameter, which, as we will see, is closely related to the overlaps. Anyway, the most important part here is that due to an absolute wonderful line of work by Guerra, Talakan, and Panchenko, it is known exactly what the optimal value of these Hamiltonians is. And it is given by a variational principle, which I will not write out here, but certainly there's a precise expression for the optimal value, which is what we refer to as GSED of psi, which is the ground state energy density of a spin glass with coefficients parameterized by this mixture polynomial. All right, just a couple of more definitions before we get into proof sketches. Multi-overlaps refer to a generalization of the inner product when we are given a list of vectors. So given L vectors over the hypercube and some index into some subset of those vectors, their I overlap is nothing but a normalized generalization of the overlap. You can verify, for instance, that if you set L is equal to 2, if so that is if you have only two vectors and you can look at this definition over both of them, it just gives you the normalized inner product between these. Now, the key connection between for generalizing the Guerra interpolation comes from the observation that the way to to parameterize the spin glass to capture the optimal value of a random CSP with any predicate F is to set up the mixture polynomial of the spin glass to be related to the noise stability of the predicate that whose instances your CSP is sampling. So for any Boolean function, it is well known that it has a unique multilinear polynomial representation called the Fourier basis. And as such, the Fourier basis gives a very clean representation for a notion of the function called the noise stability of this function under a noise parameter rho. You can think of the noise stability as measuring how robust the Boolean function is in its outputs on average to noise in its inputs. And it is written as tab rho f, and its characterization is given by a weighted combination of Fourier weights at every level of the hypercube. As we will see, this will make the relationship to the psi of the associated spin glass quite transparent. Now for the proof ideas. So the first main idea, which corresponds to theorem 1, where we try to relate the optimal value of a sparse random Max-CSP to an associated spin glass on the hypercube, is to set up this so-called Guerra-Toninelli interpolation, which is nothing but a smooth interpolation between an instance of your CSP and an instance of your spin glass. For the time being, you leave the coefficients of your mixture polynomial unsatisfied. The interpolation is such that it runs between 0 and 1, and it is smooth and preserves the variance, which is a matter of normalization. You compute the time derivative of the interpolated free energy, which I'll introduce in a second, and basically assert that for this derivative to go to 0, as alpha gets large, you get a series of constraints. These constraints are on the mixture polynomial, and they can only be satisfied if the mixture polynomial has coefficients alpha I that collect, so to speak, the Fourier weight of the predicates at every level I. In other words, you need to set the mixture polynomial of the spin glass you are interpolating to be the noise stability polynomial that we just saw, minus the constant component for centering purposes. And that allows for this derivative to go to 0. And from there, it's fairly easy to see that the maximum value of the CSP, or the optimal value of the instance of the CSP, on average will match the ground state energy of the spin glass. So to give a little more detail, the interpolation is as follows. Represent the fraction of clauses that can be satisfied by an assignment sigma to your instance I of the CSP by HIR sigma, where R is the Poisson parameter from which the number of clauses are chosen. Then for every t between 0 and 1, set the interpolated Hamiltonian to be as follows. 1 minus t fraction of the constraints come from the CSP, t fraction of the constraints come from the spin glass, and we subtract away the average value of the CSP to center the interpolation. It's quite easy to see that at t is equal to 0, you will recover the CSP. At t is equal to 1, you will recover the spin glass. So this is indeed the smooth interpolation where the endpoints are the spin glass and the CSP respectively. You compute the free energy density, which can be seen as a smoothened version of the maximum value of this Hamiltonian. And when we do this, it's not too hard to show that at t is equal to 0, so when the interpolation is squarely in the land of the CSP, if we take the smoothing parameter to infinity and appropriately normalize, we get the average optimal value of the CSP. One can then invoke concentration of measure arguments to show that the average optimal value of the CSP is surely almost surely the optimal value of any instance of the CSP where I is chosen by the given sampling procedure. And then the crux of the argument boils down to showing that the derivative of the free energy that I just defined previously can be analyzed by separating into its two contributions, one that comes from the spin glass and one that comes from the CSP. And then with the appropriate choice of psi, one can show that this derivative is actually independent of time and depends on the ratio between the smoothing parameter square divided by the clause to variable density square. A little more calculus then shows that if you choose beta to be sufficiently small with respect to alpha and take alpha to be large, the optimal values are the same. So how do you extend the interpolation to actually show overlap support equivalence? It's based on two key insights. The first is that you can define a linear map A that tells you how to couple some independent family of Hamiltonians, and a vector B that tells you how strong each of those should be coupled. You can then take the partition function, which is the sum over all configurations of the exponential of the Hamiltonian with the smoothing parameter, to be over m inputs to the coupled Hamiltonians as given by this map A, to have multi-overlaps as we defined previously, restricted to be in the support of those in the corresponding spin glass. And this is the key insight. And basically you rerun the prior argument, but with these two new insights and restrictions added, and that's it. Some more algebra gives you the result that we desire, that the overlap support of these coupled Hamiltonians of the CSP matches the overlap support of these coupled Hamiltonians of the spin glass. And now that this happens, it's not hard to show that actually you can bring back obstructions to the spin glasses as shown by Huang and Selke from to the CSP land. And I'll briefly mention this at a very high level in just 2 slides or in 2 points. So the idea, as I said at a high level, is to bring back the branching OGP framework for spin glasses as developed by Huang and Selke to sparse random Max-CSPs via this generalized Guerra-Tornelli interpolation that we just showed. To do this, what you show is that there exists a linear map A that decides how to couple these random Hamiltonians, and a correlation control parameter D that tells you how strong these couplings should be, that allows the generalized Guerra-Tornelli interpolation to recreate the branching OGP in the CSP land exactly as it is known to hold in the spin glass land, as shown by Huang and Selke. And once you've done this, you can essentially rerun the same argument that Huang and Selke have to obstruct overlap concentrated algorithms on spin glasses on these CSPs, but with some added technical constraints of restricting the solutions output by these algorithms to strictly be on the cube rather than in the convex hull, and invoking some new concentration results on the sparser instances we have rather than the Gaussian concentration results that Huang and Selke invoke on the denser instances we have, to get roughly that the same proof goes through to get the obstructions we have. All right, so that's essentially all I have to tell you as a summary of the results of our paper. Perhaps excitingly, there are a lot of open questions, but I'm going to list 2 of the open questions that are directly related to this work and came up naturally while this work was being conducted. The first is a conjecture that is imminent in some sense almost once you read the paper by Huang and Selke, or our own paper, or the prior paper of Gamarnik, Jagannath, and Wine that obstructs low-degree polynomials to a certain constant, although not alg. That all low-degree polynomials that claim to perform well in a certain technical sense and aren't just equivalent to coin flips. So the algorithms aren't just flipping coins and getting lucky, but they are doing something non-trivial, and they can quantify how well they claim to perform, actually are overlap concentrated and therefore not at all good algorithms. How not good? In that they cannot cross the algorithmic threshold of alg given by Huang and Selke. So we can give formal quantification to this notion of performing well and being far from a coin flip. And this is done in the paper of Gamarnik, Jagannath, and Wine, for instance. But showing that under these constraints, low-degree polynomial algorithms are overlap concentrated and therefore obstructed to the precise constant of alg is challenging for various technical reasons. It is perhaps potentially easier to show that these low-degree polynomial algorithms are overlap concentrated on spin glasses before, because these are denser instances and the concentration of measure results available are larger. It's perhaps more challenging to show that they are overlap concentrated on random Max-CSPs, which is the regime that we worked in this paper. And perhaps even more excitingly, the second conjecture is that there is a unifying set of sum of squares relaxations for low degree for random Max-CSPs that can match the alg threshold of Huang and Selke. There is actually recent progress. In a recent result with my collaborators, Tommaso Dorsey and Jonathan Shee, we actually show that there do exist SOS relaxations that match the alg threshold of Huang and Selke, but for a different set of problems. And perhaps the second most important thing is that we do not know is that we want to say that the multi-overlap distributions of random Max-CSPs and spin glasses are equivalent. So far, we were just able to show that the support of these distributions are equivalent. But in order to give unifying SOS relaxations for random Max-CSPs, this would be a critical equivalence we would need to show. Thank you so much for your attention.